Have you ever wondered how car makers are squeezing just so much power out of smaller and smaller engines these days? Well, a huge part of the answer is this really clever device that literally turns wasted energy into pure performance. I'm talking about the turbocharger, and today we're going to go under the hood to see how this brilliant bit of recycling actually works.
So, let's start with the fundamental problem. How do you get more power without just building a bigger, heavier engine? It's a puzzle engineers have been working on for over a century, and the answer lies in something called forced induction, which is really just a fancy way of saying you find a way to cram more air into the engine you already have. Now, you've probably heard of the two main ways to do this: superchargers and turbochargers. You can think of a supercharger as kind of the brute force solution. It's driven by a belt connected right to the engine, which means it actually leaches power from the engine just to operate. But a turbocharger is so much smarter. It is a master of recycling, harnessing the hot, high-speed exhaust gas that the engine is already just throwing away.
And that is exactly why we're focusing on the turbo. It's not just about adding a bunch of power. It's a seriously efficient energy recycling system. It captures waste and turns it right back into performance.
Okay, so at the heart of the turbo are two separate sections, as you can see right here. On one side, you have all this hot exhaust gas flowing out of the engine. On the other, you've got cool, fresh air waiting to go in. And here's the key. These two airflows never, ever touch. But they are linked by one single, absolutely brilliant mechanism. So here's how that magic connection works. That hot exhaust gas, instead of just flying at the tailpipe, is funneled in to spin a little wheel called a turbine. That turbine is connected by a shaft to another wheel, the compressor, on the other side. So as the hot gas spins the turbine, the compressor spins too, sucking in fresh air, pressurizing it, and then forcing it right back into the engine. And really, it all boils down to this super simple formula. With more compressed air packed into each cylinder, the engine's computer can inject more fuel. And more air plus more fuel equals a much, much bigger bang. And that means more power from the exact same size engine. And the speeds involved here are just staggering. To generate all that boost, the turbo's internal parts can spin up to 250,000 RPM. To put that in perspective, that's about 40 times faster than your car's engine at redline. This tiny little pinwheel is rotating over 4,000 times a second, all while being blasted by incredibly hot exhaust gas. It's just an unbelievable feat of material science. But, this technology wasn't born on a racetrack. Its history actually begins much, much higher up, solving a completely different problem. Let's take a look at how the turbo evolved from the sky to the street. The turbo's journey took decades. It was patented way back in 1905, but it first found a real use on these giant diesel ship engines. Then it took to the skies in World War II, made a pretty brief appearance in American cars in the 60s, and then, finally, became a total legend in the 1970s thanks to brands like Porsche, who made it synonymous with extreme performance.
That application in the skies was a complete game changer. See, at high altitudes, the air is really thin, and it starves a normal engine of oxygen, causing it to lose a ton of power. A turbocharger completely solves this. It compresses that thin air, essentially making the engine think it's still breathing thick air down at sea level. This gave planes like the B-17 bomber a critical performance advantage.
But when turbos finally made their way into cars, this really annoying side effect became obvious. A phenomenon that drivers came to dread, something called turbo lag. Turbo lag is that frustrating pause. You step on the gas and nothing, just for a second. Then, suddenly, whoosh, the power kicks in. That delay, that's the time it takes for the exhaust gases to build up enough pressure to spin that little turbine up to its effective speed.
So for decades, the holy grail for engineers has been to eliminate that lag, and they've developed a whole arsenal of clever tricks to do it. From using ultralight materials like ceramics to designing these incredibly complex systems that can actually change the turbo's behavior on the fly. So two of the most common solutions you'll see today are twin-scroll and variable geometry turbos. A twin-scroll design is kind of like giving the exhaust gas two separate lanes to the turbine, which helps it spin up way faster. And a variable geometry turbo uses these tiny moving vanes inside it, allowing it to act like a small, quick turbo at low speeds and then a big, powerful one at high speeds. Both are designed to give you power exactly when you ask for it. No more waiting.
All of these innovations bring us to the present day, where the turbocharger is more common and more relevant than ever before, but for a totally different reason than just pure speed.
Yeah, these numbers really tell the modern story of the turbo. Today, it's not just about going fast anymore. The huge adoption we're seeing, especially in places with high fuel costs and strict emissions laws, is all being driven by a quest for efficiency. The goal has shifted from just making more power to making power smarter.
And this right here is why it matters to pretty much every driver today: engine downsizing. Manufacturers can now build a tiny 1.5-liter four-cylinder engine, add a sophisticated modern turbo to it, and get the same horsepower as an old, thirsty 3.0-liter V6. And they do it while using way less fuel and producing fewer emissions. It's the definition of efficiency without sacrifice.
So, when you think about it, the turbocharger is just a testament to brilliant engineering, a device that took useless waste heat and pressure and transformed it into efficiency and power. And it really makes you wonder, as we keep looking for new ways to be efficient, what other sources of waste energy are we overlooking that could power our future?